So we talked about the combustion sources of energy last time, and in so doing, we talked a little bit about renewables, we talked about solar, but we didn't get into the details of solar. And one of the items on there was nuclear. And so I like to take this advantage here at the end of PChem thermodynamics to really dive into the energy that's stored in the nucleus. That's a very thermodynamic thing. Like what kind of energy density are we talking about? When y'all did the QSPR lab, uh, you calculated the energy density, like how many kilojoules per gram of substance could you get? And you just won't believe how much energy is in the nucleus. I mean, really, if you were to put your mind to it and think, here's all our sources of energy, the fossil fuels and so on, and then you look at what's in the nucleus, it just totally is a game changer. Okay. But before we get there, we need to talk about the structure of the nucleus and the nuclear transformations. And so this is just an introduction to all the different nuclear reactions that take place, and really just shining a magnifying glass on the nucleus and see what's going on down there. Okay. So you probably learned some of this stuff in Chem 1, like we have our elemental symbols that we have on the periodic table. We still call them symbols, even though they're letters, right? But that dates back to alchemy. Do y'all know this? Like in the alchemists, they were trying to find a recipe to make gold. And so they were trying to hide their work. Like if you stole my notebook, you could look through it, but I wrote everything in symbols. So there was like little symbols for mercury, symbols for this, or symbols for that. And so this idea of each chemical having a symbol has just sort of been the way we think about it. So those are our chemical symbols. And so this is the symbol notation. The letter and the number of protons really go together. So that upper right hand corner, you see all of the numbers there. Those are the number of protons in the nucleus. And so a lot of times we will omit the atomic number, but this is the atomic number in green here, number of protons. Okay, so number of protons, and like if you got 6 protons, it's got to be a carbon, no matter what, right? Number of neutrons, that just changes the isotope. But if it has 6 protons, it's a carbon. And if it's a carbon, it's got 6 protons. So a lot of times people will just omit the 6 and they call it carbon 12, because the 12 piece is the total number of particles in the nucleus. And that's a pretty good proxy for the mass of that particle. So carbon 12 actually defines the whole mass of the periodic table and all the other elements. We have a carbon 12 system. So we've sort of defined the mass of carbon 12 as 12. Now this was defined before we realized that there was a slight difference in mass between the neutrons and the protons. Okay, so when we could have probably had like a new definition to define the proton as a mass of 1, and then the neutron mass would change, and go on a carbon 6 system and say the mass of carbon is 6 grams per mole, and we would just have a different number defined as the mole. So anyway, but the mass number is the total number of particles in the nucleus, so that's protons and neutrons added together. And so if you wanted to know what the neutrons were, if you write it like this, you just subtract the protons from the neutrons and you get, protons from the total and you get neutrons. All right, so it's really kind of nice. It's set up there. So that's what you need to know if you're going to find out the number of neutrons. So a carbon 13 would have 7 neutrons. A carbon 14 would have 8 neutrons. The mass number is what defines the isotope, and so we would call that carbon 12 or carbon 13 or carbon 14. You see here, this is the chart of the nuclides, and it's great. I always wanted in our chemistry department at UT, we had like a wall chart with all of the isotopes, the chart of the nuclides. Now it's online, of course, but you can go in there and you can see. Here's the row for carbon. So number of protons, 6. So all of these right here are carbon atoms. Did you know there was a carbon 9 and a carbon 17? It's kind of strange to think about, right? Now, these things don't last very long. Carbon 17, the half-life is 191 milliseconds. Okay. So 10 half-lives, it'd be gone in like 1.9 seconds. So all of it would be gone and it doesn't stick around very long. But carbon 12 and carbon 13 are stable. So it has an unmeasurably long half-life. If it, we call it stable. Carbon 14, 5,700 years. So in this chart of the nuclides, you can see the half-lives on all of those. You can also see how they decay. This beta right here means this is 100% beta decay. So when it goes from a carbon 14 to some other more stable element, it spits out a beta particle. Other particles, other nuclides will spit out alpha particles. Like here's beryllium 8. And beryllium 8, 100% alpha. And let's see, I'm not sure what it means by 5.57 EV. It's listed in the half-life spot, but yeah. EV is electron volts, but I don't know why that's listed in the half-life location. But we can go to the chart of the nuclides, and we can play around with that later. We can go there and look. Now, obviously, the horizontal axis on this chart is something related to the neutrons, and it would be the neutrons. So this would be the 14 neutron row, 14N. So all of these elements have 14 neutrons. And then 15, 16, 17. So each column is a different number of neutrons. So the neutrons, their role, as far as we can tell, stabilize the nucleus. Now, if you think about what Rutherford did, he shot alpha particles through gold foil, trying to test the different theories about the nucleus or the atom at the time. They had discovered electrons. J.J. Thomson and Chadwick had discovered, J.J. Thomson actually had discovered the electron and the charge to mass ratio of the electron, and verified that it was a particle. It behaved like a particle. You could steer it in a magnetic field, and it was in discrete units with the oil drop experiment and so on. So we thought, okay, we got electrons that are particles. How does the structure of the atom fit? And Thomson came up with what's called the plum pudding model. He said, what's going to keep these electrons stable in a nucleus? If they're surrounded by positive charge, then they don't really notice each other, and you can get electrons. Like if you look at gold here, 79 protons and 79 electrons. So how do we get 79 electrons in there without them blowing each other out of the atom? So he said, well, the electrons are like the plums, and the pudding is this positive charge. So that was his theory for the atom. It seems silly to us because we know now what a better theory is, but he didn't at the time. So Rutherford was testing this, and his alpha particles, some of them deflected back. And he said it was like shooting a howitzer at a tissue paper and having it ricochet. Most of them went through with very little deflection, but some of the alpha particles ricocheted back at large angles. And what we're seeing here are alpha particles coming out of a nucleus. This is a radioactive object. This is a cloud chamber. And you can see the alpha particle tracks creating little nucleation paths. So you have a vapor, and ethanol is typically used, of supercooled ethanol gas. So we've cooled the ethanol gas. It's supercooled. It wants to condense. But it's just waiting for something to draw those molecules together, like a charge. So this alpha particle that's charged will come screaming through that supercooled gas and create kind of like an ion trail that will cause those molecules to condense and create a little track. So this is what a cloud chamber is. And so we can see that this element here, this rock or a piece of ore, is radioactive, and it's sending out tons and tons of alpha particles. So Rutherford used those alpha particles to probe gold foil, and he noticed that some of them, they're coming out fast. Notice some of them were deflected largely. He said, therefore, most of the mass of gold has to be concentrated into a very small package called the nucleus. And the only way, which sounds like a stupid idea, think about it. You've got positive charge and you have it smeared across this huge atom, or you're going to concentrate it into a small dense package. What's going to get positive charges together when positive charges repel each other? right? We got 79 individual electrons roaming around, and you're going to take all the positive charges, and instead of like coming up with some structure where the positives and negatives cancel each other out, like think of a salt crystal. You've got chloride ions and sodium ions. And what's the structure of the salt crystal? It's not all the sodium ions in the middle with chloride ions orbiting. It's sodium chloride, sodium chloride, sodium chloride, where all the positives and negatives can kind of nestle up to each other and cancel out their charges. So that would make more sense. No, Rutherford said no, because of this deflection, all of the mass has to be collected into a small package. And so you could only do that with a new force of nature called the strong nuclear force. So he just comes up with, because of this mass effect, he just comes up with a new force and says, all right, we got a strong nuclear force that overcomes this positive charge and holds everything together. And now we know that it's the neutrons that play a role in stabilizing that positive force, because otherwise the protons would blow each other apart. Okay, and that's what happens with unstable nuclei. Why do these alpha particles shoot out of the nucleus? Because you got too much positive charge, and the neutrons aren't able to stabilize all of that positive charge, and some chunks of it blow out of the nucleus. And so these are the naturally radioactive elements, and you can see they're the big ones. And once you get above a certain level, like 84, once you get above bismuth, then everything is radioactive. So those nuclei, there's just too many protons in the nucleus, and they're unstable. Okay, so then they just start falling apart. Now there's a couple of weird ones like promethium and technetium. This is one of the last, setting aside all the man-made elements. This was one of the last naturally occurring elements that ever be discovered because it was so hard to purify. Right? You collect an ore, you try to purify it, and while you're trying to purify it, this element is decaying away. And so it was a very difficult one to find. But once Moseley connected the 1s electrons to the number of protons in the nucleus and came up with an X-ray model, then we were able to find elements really rapidly. So let's go through the different types of nuclear transitions. We just saw alpha emission. So if that was a uranium ore sample, this is what's happening to create those alpha particles. So you see in all of the reactions, you want to write all these down. So we have uranium, and if I say uranium decays by alpha, this is what you know right here. So you can write uranium. You need to know what isotope it is. The 92 is given because I'm talking about uranium. But this is what you need to know. So you need to know what isotope. So uranium-238, and it's decaying by alpha emission. So an alpha particle, by definition, has 2 protons. It's the same as a helium nucleus. And I'll go ahead and put the charge up there. Helium 4, 2 plus. And if you look at helium, 2 plus means you've only got the nucleus. We've stripped all of the electrons off. So it's just a helium nucleus. So it's come shooting out of the nucleus of the uranium-238. And now here's the arrow. So you just balance everything. So the protons have to balance. And so if I've taken away 2 protons, then I've got to have 90 protons left over. And so 90 plus 2 is equal to 92. And once I have 90 here, then I know it's a thorium. So looking at the periodic table, you've got, I'm over here, uranium. And if I throw out an alpha particle, I move left 2 spots. Because alpha particles always have 2 protons. So if I've lost 2 protons, I move left 2 spots. What happens to thorium if it spits out an alpha particle? It's at 90. So we got to find somewhere on here 88. Okay, 88 radium. What if radium spits out an alpha particle? We go from 88 down to 86. Now we're at radon. So all of these alpha decays, you just jump left 2 spots on the periodic table. Radon spits out 2, you get polonium. It spits out 2, you get lead. And then you're at a stable element. So almost all, maybe all, the lead in our environment has come from alpha particle decay of these really heavy elements. Yeah, it'll go down until it hits a stable element. And so you can see up here, you see once we get below bismuth, we hit lead, then we're stable. And so the half-lives vary, but they spit out these alpha particles, boop, 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 and then you hit lead and you're there. Yeah. So that's where most of the lead, if not all of it, came from. Okay, then we have beta emission. That's another decay route. Oh, well, let's do the total number of particles too. So everything has to balance. If the alpha particle has 2 neutrons in it, which it does, then you got a 4. So we've lost 4 from 238. And so if you subtract 4 from 238, you get 234. So this is the particular isotope of thorium that we have. Now I put this in here just most of the time they don't show this, but there's energy of the alpha particle that comes out, there's the energy of the thorium nucleus, and those rarely balance perfectly with the uranium-238. And so there's also a photon of light that's spit out. And so gamma rays come out of almost all of these reactions. And so I throw that. But there's no mass to a gamma ray, but it is an energy balancer. So when you add up the energy of the products and reactants and the kinetic energy, if you know it, of the alpha particle, the missing energy could be released as a gamma ray. What's that? Well, like the alpha particle plus 2, now you've got a uranium nucleus that's -2. It becomes a thorium -2, and then if you were to able to like keep this little environment stable, then that helium or alpha particle, if it slows down, would take those 2 electrons and become a helium gas, and then the electrons would all balance out. Yeah, yeah. But you could see from those tracks that alpha particle is way far away from the nucleus it came from. So there is a charge effect going on too, but the energetics of electrons are so minuscule compared to the energetics of the nuclear decay that we ignore it. So we ignore the chemistry that's going on. When we think of chemistry as being an electron cloud interactions, we just ignore all of that because these are so energetic. Yeah. But I've often thought, if you could, blast the alpha particles at a surface that would capture them, you would set up a charge differential, right? The source that it came from is negative now, and the place where the alpha particles are going is positive. And so you might be able to get direct route to electricity. And to my knowledge, that's never been exploited. So there's a source of electricity here that no one's exploited. If you would need to get a decent amount of current, you would need to have an extremely radioactive substance. And so the amount of energy coming out of the nuclear transformation would be way greater, and the heat released way greater than any electrical current that we could get out of it. But for maybe these we make micro machines now, maybe there's something there that could be exploited. I don't know. Here, and beta particles too are energetic electrons that are shooting out of the nucleus. So this is kind of a weird one. This beta particle, this is the same as an electron, okay? It's treated as a -1 proton, and it's treated as really no particle. It's not a neutron, it's not a proton, and so it has a 0 mass number. I'm going to put that in quotes, no mass, right? It does have a mass, but it's 1,000th of the mass of a proton. So 1,000th, it's really insignificant. Okay, so in terms of the impact on the nucleus, it doesn't count as a nucleon, a particle in the nucleus. When it leaves, it converts one of the protons into the, it converts one of the neutrons into a proton, okay? So to balance this out, we've got 53 protons in iodine. Over here, we got a -1 on the beta particle. And so those are the 2 pieces of information you need. And so you need to have a 54 added to the -1 to get it to balance to 53. So the proton line has to balance. And so does the neutron line. So 0 nucleons left the iodine, and so 131 equals 131 plus 0. So that's the beta emission. It's an energetic electron. And what happens? Okay, so look at iodine right there. If it undergoes beta decay, it becomes a xenon. So beta decay moves everything to the right one spot, just one spot. Alpha particle jumps left 2 spots. Beta decay moves it to the right one spot on the periodic table. Because what's happening is really a neutron is spitting out an electron and becoming a proton. That's weird, right? So it looks like an electron plus a proton, if they were able to get together, the charges would cancel and that proton would become a neutron. And that's what happens too. So.
How often, like, does that also stop at night or just?
Yeah, so the beta decay and alpha particles, they really don't happen on anything below polonium. So bismuth on, except for technetium. So none of those others, yeah, once it hits lead or any of the stable elements, then it's, yeah, it's
So
done.
for technetium, does it just go?
I can't remember. Well, look, we can look at the chart of the nuclides and see what technetium does, if it's a beta or alpha emitter. Yeah. Now, this is a positron, so you could have, this is where we get into antimatter, which is very strange. You can spit out a beta particle, but you can also spit out a positron, and that's an anti-electron. So it has all the properties of an electron, except it has a positive charge instead of a negative charge. That's weird. Yeah. And some elements like carbon 11, notice it's not carbon 12 or carbon 13 or carbon 14, it's carbon 11. You could think of it as having more protons than it can support. Like the neutrons, you only have 5 neutrons, and they could really stabilize 5 protons, and here we have 6. And so in this case, one of those protons spits out an anti-electron and becomes a neutron. And so again, 5 plus 1 equals 6. And then the electrons, whether they're beta particles or positrons, have 0 nucleons associated with it. So 11 equals 11. And so this is what we have for positron emission. And you think, well, that seems strange, but have you all heard of positron emission? Yeah, positron emission tomography. This is a scanning technique that we use in medicine. We'll talk about the medical applications of this in the future, but with nuclear reactors, we're able to isolate enough carbon 11 that then we can put that into sugar molecules, it's carbon, feed it to people who have cancer, and scan where the sugar is being absorbed. And cancer cells love sugar. So since they're multiplying so fast, they're building structures, they're voracious consumers of sugar. So they glow like crazy with the positron emission. It's, we'll see an annihilation experiment here in a second, or one of the further down there. So let's do electron capture, and then we'll get to annihilation. Well, no, since you asked, let's do annihilation next. Okay, so here's an electron, and here's an anti-electron. And if those ever get close to each other, obviously positive and negatives react or attract. They're incredibly light, so they can change direction very rapidly, right? Because they're very small. And they will crash into each other. When they crash into each other, they annihilate. The mass disappears and turns into energy. So that's why you have matter and antimatter. If you can combine matter and antimatter, the mass is completely converted into energy, and you get 2 gamma rays that come out. So those 2 particles cease to exist and become light waves. This is a weird world, isn't it? So, and that's what's actually giving, when I said the tumor glows in a PET scan, it's the 2 gamma rays that come out. So the positron comes out, and our bodies, I mean, all matter is mostly matter, not antimatter. And so as soon as that electron or positron comes out of the nucleus, it finds a regular old electron, and they annihilate each other, and you get 2 photons that come in. So that's the annihilation. I talked about if you could combine an electron with a proton, then it would become a neutron. And that's what's happening here with electron capture. And this is another decay path. for the really heavy elements. So you think about uranium-92 and think about those 1s electrons, right? They're the closest to the nucleus. So you've got two little electrons trying to stay out of the nucleus that has a mass of 92, I mean, a number of 92 protons. So you got 92 positive charges, and you got this nice little electron that's trying to orbit and stay out of the nucleus. And occasionally it gets captured by a proton and turns that proton into a neutron. So here we have the electron. Again, it sort of cancels out one proton, so 92 minus 1 equals 91. And so this becomes protactinium. It doesn't change the mass number at all, so 234 plus 0 is 234. And then we have an energy balance gamma ray that comes out. Okay, one more. This is the last one here that is sort of naturally occurring. So all of these naturally occur. Well, I can say all of them. The next one does too, but this is spontaneous fission. And some elements just undergo it spontaneous. So you've got spontaneously. So here's uranium-234 and 92. It can spontaneously break up into a variety of elements. So it's not only xenon and strontium, it's anything that adds up to 92. So 54 and 38 add up to 92. Add up to 92. And so there you can pick any two numbers that add up to 92, and you'll get those two daughter elements from spontaneous fission. Now there's a distribution, like you could do a histogram of those different kinds of elements, and you could see that there are some preferred elements, but there's not only two. You know what I'm saying? You've got a sample of uranium-234, you're going to get a distribution of daughter elements. But again, you just mass balance everything out. Also, you need to know this. This is something that you have to look up. These spontaneous fission reactions may produce one neutron, a spare neutron, maybe two, maybe three, maybe none, I guess, in theory. And so there's no way to know necessarily how many spare neutrons are going to come out of a spontaneous fission reaction. You have to do experiments and try to do a neutron balance to see how many neutrons are produced in spontaneous fission. But once you have this number, then you know there's two here. There's two nucleons captured in those two neutrons. And so in this case, these two numbers have to add up to 232, and then you get two more for the neutrons, 233, 234, and so then that balances out. So in order to get these two numbers right here, you would need to know this number two. Mm-hmm. And so so you could go look at the chart of the nuclides to see which one of those is more abundant. Yeah, and so that would sort of tell you how likely it is to form the xenon 131 versus xenon 130 or xenon 129. It's going to be a bunch of different xenons. And that chart of the nuclides will be a good place to go to kind of see what the odds are of which one of those is produced. Yeah, that's how I would do it. There may be a better way. We're getting right at the edge of my knowledge in terms of nuclear physics, and so I don't exactly know if there's a better way to figure out which of the two elements would be produced. And then this is stimulated fission. This only occurred after, well, I guess we discovered this in terms of trying to make a nuclear weapon. We were trying to find, is there a way to stimulate the fission reaction? And we noticed that if you hit these nuclei with a beam of neutrons, then you can stimulate fission. So spontaneous fission And spontaneous alpha emission and spontaneous beta emission, those are natural processes, and they're going to follow first order kinetics. And there's really nothing environmental that you can do to make those half-life change. So uranium or iodine 131 or whatever, they have stable half-lives that you can look up. Okay. And the temperature doesn't matter, the pressure doesn't matter, because all of this is in the nucleus. But you can destabilize the nucleus. You can hit the nucleus with particles, like a neutron. So if we bombard the nucleus with a neutron, then we can make it split faster. So spontaneous or stimulated fission is stimulating the nucleus to break apart. So we're changing the half-lives. The half-lives are natural half-lives. This is just based on the neutron flux. If I throw more neutrons into the mix, then I'm going to get more fission. And so now we're adding a neutron, we're getting it to split, and now we have 3 neutrons produced because we put 1 in and we got 3 out. And this allows us to use these 3 because we have a multiplication of neutrons. These neutrons can hit other nuclei, and we have the possibility of a chain reaction. So we can start this process, and if that process of stimulated fission creates more neutrons, then it can become a chain reaction and it can actually run away. If you can control it, it's a power plant. If it runs away, it's a bomb. So there's the difference between the two. It's the same process. It's stimulated fission. And then we have nuclear fusion. So this is the last one that we know about. You can combine certain nuclei if you can overcome the repulsion of the nuclei. So if you get the nuclei close enough, essentially the distance is unclear to me, but it seems to be when the nuclei touch. That's how close you have to be. So when they touch, to me, I think of it as a water drops. Like you get these water drops and they repel each other, and then when they touch, they absorb and become a bigger water drop. So here, this is just one of the nuclear fusion reactions that actually surprised us. We were trying to fuse deuterium. This is heavy hydrogen. So it's got 1 proton, but a 1 neutron. So this is deuterium. So if you look for D on the periodic table, you're not going to find it, right? But this is just the symbol that we use for deuterium to set it aside from hydrogen. You could also just put a hydrogen there, an H. With a 1 and 2, you know it's hydrogen 2 instead of hydrogen 1. So this is deuterium. They were doing a nuclear test. I think this one was called Castle Bravo. You can look it up online, the first fusion test. They were trying to fuse this deuterium together because they knew if we got 2 deuteriums together, it could make a helium-4 nucleus. So they were trying to go from D2 to helium-4 by just fusing the 2 helium nuclei. So what's one way to get hydrogen in a really dense form? You could cool it down and make hydrogen liquid, or you could make lithium deuteride. Okay, so you could just put it in a salt form. So lithium is enough of a cation that it can get hydrogen to act like an anion. So it's Li plus and H minus. And now you've got a solid form of hydrogen. That's pretty cool. And you've got all this deuterium, I keep saying hydrogen, but deuterium in this lithium deuteride salt. And then they blasted it with neutrons and pressure from a nuclear blast. And it was way more energetic than they expected. And in fact, there was a barracks a few miles away from ground zero, and they thought, they did the calculations. The barracks would be fine. It's not, it's far enough away that the blast isn't going to get near it. But because they didn't know about this reaction, the barracks were destroyed. But at the last minute, they thought, let's be safe and let's pull all the men out of those barracks. And they did. And the barracks building was knocked over because there was a second fusion reaction they didn't know about. And so this lithium and deuterium, which they made lithium deuteride, could fuse too. And they didn't know that those 2 elements could fuse. So here we've got lithium 7 and deuterium coming together to make 2 helium nuclei, and those protons balance. 3 plus 1 is 2. The nucleons almost balance. 7 and 2 is 9. Here we have 8, and so it produces a neutron. And then the neutron can be used to do stimulated fission, And so fission, fusion always go together. We can't get fusion without fission. Now we're trying, and we have reactors here that are trying to get to fusion energy, and China is boasting too about some of their reactors. But we know how to make fusion. You need incredibly high temperatures and incredibly high pressures, and you can get those from fission. So you can make a fission bomb that produces a fusion bomb. And then the fusion bomb can generate neutrons that go back and keep the fission going. And the fission can create the pressure and temperature we need to do the fusion. So these two go together. We can use fission for power, and not just bombs, but nuclear power, but we're trying to get to fusion for nuclear power. So whenever you hear people say, well, at current technology, the world's going to end tomorrow or whatever, we never stay at current technology. Nuclear fusion is a whole area of energy that we still haven't captured for power purposes. We've captured it for destructive purposes, but not for power. So these neutron to proton ratios are really important. It starts out at 1:1. If you look at the periodic table, you can see, let's just look at carbon. Carbon has 6 protons, but the mass is 12. Okay, 1:1, 6 neutrons, 6. Look at nitrogen, 7, and the mass is 14. Oxygen, 8, and the mass is 16. So this 1:1 ratio of neutrons to protons works really well for small nuclei. But as you get more and more positive charges, it starts to transition over to 1.5. So this belt of stability really follows a 1.5 neutron to 1 proton ratio. And so that's what we call this belt of stability here. And so if you have too many neutrons, you can do beta decay, because if you look at what's happening here, you're going up, and this is protons on this axis and neutrons on this axis, and you're moving up towards the belt of stability. So if ion spits out a beta particle, it becomes xenon. It's moving up, like straight up, and it'll eventually get to some element that's stable. If you have elements that are above the belt of stability, they have too many protons, and so they could spit out a positron, and that would move them down, straight down, okay? They could also capture electrons, and that would move them left, okay? And then alpha emission, if you have too many nucleons, a total, like your nucleus is just too big and too unstable, you can spit out an alpha particle, and that moves you diagonally here at a slope of 1, and you're going to eventually get into the belt of stability. So here's an example of that. So we can start with uranium. Now this has a slightly different path in your notes, and the one in your notes is incorrect. I corrected this morning. So you notice how your notes shows on the x-axis, that's the number of neutrons, okay? It's the number of neutrons. When I made the figure in your notes, I was using a different chart. I had updated the background chart, but the chart that I originally had was out of the freshman textbook, and it had total number of particles down here instead of just neutrons. And so if you look at those arrows, they go left 4 spaces instead of just 2 in your notes. And they should really just go left 2, because we're dropping down 2 neutrons and dropping down 2 protons. And so we have this steeper path here. So this is what's called the uranium decay path. So we start up here at uranium, and it spits out an alpha particle, it becomes thorium. And of course, thorium could spit out an alpha particle and become radium, but it could also decay by beta emission. So beta to protactinium, beta, now we're back to uranium, but we're a different isotope of uranium. And then alpha to thorium, alpha to radium, 2 more betas, now we're back to thorium, and then we have a run all the way down to lead. Thorium to radium, radium to radon, radon to polonium, and polonium to lead. And then this is not a stable form of lead, so it spits out 2 betas, it becomes polonium, and then you get another alpha, and now we're at a really stable form of lead. We can, well, let's see. Let me just show, one of the things that we've discovered too is you can find like a uranium ore, and it has like a uranium to lead ratio, right? And a bunch of daughter elements too. And then it's got damage in the surrounding rock. And these are called alpha halos. So as those alpha particles have come out into the surrounding rock, they've damaged the rock. And we know the half-life of uranium. And so we can look at this and we can say, wow, we know all the alpha particles that came out of this uranium ore. We can measure the amount of lead that's there. We know the decay rate of uranium. And this is a way to date that rock, and a way to show that that rock is really an old rock. Okay, so this is some of the ways we know that the rocks that we see in geology are really, really old. Now we can do some of these, we can do some fun things with these charged particles that are spit out of the nucleus. And we can, how do we, like Rutherford, how on earth did he get a beam of alpha particles, right? And what can we do with those? Well, let's say we have a little particle source that spits out an alpha particle. It's positively charged. And so over here we have maybe a negative magnet, and so that positive charge is attracted to the negative magnet. But before it hits that magnet, we switch that magnet to positive, and we, switch that little electric field to positive and make this field negative. So, and then we put this in a magnetic field. The magnetic field causes the positive charge to do a turn, and then we can alternate this voltage source to attract or repel the positive particles. They will accelerate, and as they accelerate, they get a larger radius in this path because they're going faster and they can't turn as fast. And so this is a way to accelerate these particles, and then we can shoot them at a target. So that's how a particle accelerator works. You have a source of the particles, and then you carefully accelerate it in a vacuum, in a magnetic field, which causes them to take curved paths. And then you alternate this voltage to attract and repel and keep it going. And you ramp that voltage up, and they get faster and faster and faster. Okay. It is very much like a mass spec, yeah. And then this is the one we have in Chicago at Fermilab. And so down here we have these injector rings. And so the little tiny one is here, gets it going at a certain speed, and then it puts it into a bigger one. And then it injects it into this one. Now, why the long path? Well, think about it. Those particles are going faster and faster. We need to alternate the voltage to keep up with it. And our electronics are limited in how fast we can change the voltage, right? Because you're trying to charge up this plate and then sink that charge and go negative. You got to move those electrons. That's an enormous amount of current. So there's a limit on tiny little plates. So we want to spread this particle out to where we have time to change the voltages and keep that particle accelerating. So we just use distance. We have the whole thing evacuated so the particle can go without bumping into anything. And we just steer these particles with electric fields. The further the ring is, the bigger the ring, the faster we can get things going because we can change those voltages. And so this is the one in Chicago. There's a bigger one in Switzerland called CERN. And one physicist said it's kind of like trying to studying the nucleus is kind of like studying a watch by smashing it against the wall and picking through the parts. Okay, because we can get particles going in opposite directions, which then doubles the speed when they hit, right? So we could have a static target and hit it at 100 miles an hour, or we could have two targets going in opposite and hit it at 200 miles an hour. And so that's what we have. Here's the CERN in Switzerland. You can kind of see one part of the arc here, it looks like, underground. And then how do we determine what's happened? Well, we have these bubble chambers. So what I just showed you earlier with the bubble chamber, they make really huge ones and insert all kinds of light detectors around it and photographic equipment. And so these particles are hitting each other and they're creating charged particles, and you've got magnetic fields. And so if you know what the magnetic field is, and you can measure the radius of curvature, then you know the charge in the particle. So, and the mass. Okay, so you got a charge to mass ratio that will give you the different properties of the particles. And sometimes you get other things like this lambda here, where particle has decayed and split out into two particles and so on. So this is how we've deciphered all of the quarks and particles in the nucleus, the subatomic particles. We won't get into that because again, it's a fascinating stuff. You can read it on your own, but this is a thermodynamics class, and so we really want to just focus on the energy that's available in the nucleus. So this is fascinating stuff, but again, we're going to stick to the thermodynamic side of things. But I couldn't really talk about the energy in spontaneous and stimulated fission or fusion without you understanding what alpha decay is and beta decay, and that nuclei can hop all over the periodic table, right? So now that you know that, we're going to get into the energetics of the nucleus and the medical uses and so on. So the best part of the whole course, I think, is here at the end.